So, typical sort of setup for an internal resistance problem, the dotted lines around here show, I suppose, the true representation of the battery. This small R here, that's your internal resistance caused by chemicals within the battery, the resistance that they cause to the electrical current. This voltmeter here is connected across the battery before it's connected to anything whilst the switch is open, and then when the switch is closed it will also measure the voltage across the circuit. This current will measure the current that flows through the circuit. Remember that current will be the same here in the external part of the circuit as in the internal part of the circuit, which is inside the dotted box there. So initially when the switch is open the voltmeter reads 2 volts, so that's when no current is flowing, and when the switch is closed it reads 1.6 volts when current is flowing, and the current here is 0.8. So as with the examples I was showing you, the best idea is to write down all the things you know first of all for your internal resistance equation. E for EMF, I for your current, big R for your external resistor, small r for your internal resistance, and then V for your terminal potential difference. So when the switch is open, that voltmeter is only connected across this battery, so therefore no current flowing. That's going to be your EMF. So EMF here is 2 volts. When the switch is closed, you close the switch and that value goes down. It goes down because of the internal resistance in the battery here. So you've got 1.6 volts, so that's your terminal potential difference. V is 1.6 volts, and I is your current of 0.8 amps. At this stage we don't know the 2 R's. So part A, the question is, what is the EMF? And then part B, what is the TPD? So we've already figured that out. The EMF is 2 volts and the TPD is 1.6 volts. Therefore, in that case, the lost volts is 0.4. Part C, calculate values of R, big R and small r. The easiest way to do this is to split it into the 2 parts of your big internal resistance equation, which remember is either this or this. This here, remember, that's your terminal potential difference, V equals IR, and this here lets you calculate what your lost volts is. So in this case we have everything that we need. We've got the current and we know the voltage and we know the EMF, so we can split it off into its 2 parts. V equals IR, that's terminal potential difference, equals current multiplied by big R, the external resistor. That's going to be 1.6, will be equal to 0.8 multiplied by big R, so big R is therefore 2 ohms. In order to calculate what the internal resistance is, we use V equals I times small r. That V there is your lost volts from over here, so that's 2 minus 1.6, which is 0.4. That's your 0.4 here. Still got 0.8 amps flowing because it's the same all the way around the circuit. Use that to calculate small r, you'll get small r as 0.5 ohms. So you've got values of big R and small r there. Just got one more part to answer, which is a wee bit more complicated. The new readings, calculate the new readings on the ammeter and voltmeter if R is half. So our value for big R is half. It was 2. Calculated that as 2 here. It is now 1. So that's going to affect our current that's in the circuit. So we calculate current first. That's the easiest thing to do. You can do that because you've already got everything you need. So you've got I is what you're looking for. You've got big R. It's changed. Internal resistance. That's something that's never going to change. You know, if you know the internal resistance of a battery, it's always going to have that internal resistance. That's just due to the chemicals in the battery. That's not going to change due to a change in external resistance. So this still remains 0.5. That's really what that question is designed to test. EMF is still 2. Again, that's something that does not change. That's the amount of energy the battery has before it's connected to anything. So it's I multiplied by 1 plus 0.5 this time. So 2 will be equal to 1.5 I, so therefore I is 2 divided by 1.5, so you get I as being 1.33 amps. So you've got a new current that will affect the amount of voltage that is used up, the amount of energy rather that is spent on the external resistor. So you can use V equals IR for that. It's quite easy now because 1.33 multiplied by 1 is going to give you your 1.33 volts, or 1.3 volts would be fine as well there. So the current has changed, the current has gone up. The reason the current has gone up is because this value of R that we have in the circuit, this value of R here has gone down. So if that value has gone down, then it means that the current that's flowing through the circuit, current that's flowing around the circuit, doesn't have as much stuff in its way. You know, the circuit isn't going to resist the current as much because that value has gone down. So therefore, your value of current goes up. So if the value of current goes up, that therefore has an effect on the lost volts as well. Because the lost volts is equal to V equals I times small r. If this stays the same, but this current goes up, then this value of lost volts is going to go up. So that's why your terminal potential difference is less than it was before. It was 1.6, it's now 1.33, so there are more lost volts. There are around 0.7 volts, lost volts, because this current has gone up, internal resistance has remained the same, so therefore the amount of lost volts goes up, because it always must add up to that EMF, which was 2 volts in this case.